basically, my first speech, you want to do it in ICB. Basically, IVF is basically the deprecated one. There's no, we don't have in vitro. We have in glass. We don't have in vitro. We have in chamber. So this is in chamber fertilization. So basically, I'm trying to get IVF as the blueprint for ICB. But this is day five. Basically, the human blastocyst like day five. This is how the gametes mate. So you get the inner wall. The but this is basically based on Creation's model, but in the physical form. So let's call it basically you got the mind qualia, the bubble qualia. This is the physical bubble qualia. But this is the bubble qualia, but in physical form, which is your body, your hands, your soul. So before I distill all of this, let me give you why this matters. So the bubble is there. The bubble is there, which is the embryonic cell, the egg and valute fertilization. Trying to build like a chamber system. So it's like a chamber, but it has all the best new things, for it. It contains everything and beyond the baby we need to get to go to life for everyone else. Everyone is a human being. For example, mosquitoes and flies, all the intimate, give disease, all that's vermin, all these things that cause disease for us. We can separate us from the vermins, the rats, without any cat, because when we have a cat, you can give them an injection, and when they eat the rat will die. But not just die, the whole population of rats will decline. Because when a cat gets more change the genital of a cat without changing the genital of you, you are indirectly affecting the species because you are giving cats more testosterone to kill mice. Those kind of things are really important. You don't basically you don't interact with the mice directly. You interact with the hierarchy, the biome around them. Cats eat mice. Mice eats whatever they eat shit, rubbish. What is important? So basically, what does mine eat? I don't even know. Mine eats birds. Some of the birds. Rats. Basically, mine eats anything that's dirty. Anything that's trash. But yeah, what are trash? With the ER foods too, because they lack our food. So basically, you can have pets there, but this kind of hierarchy I'm trying to get. So this is very important to do because you can do that at the genetic level, which is the embryo of the cats, mice, dogs, all the things that are indirectly we can control, so we don't get a population increase or decline without affecting the whole tier. Everything is with mice directly. That's their problem. So we make sure their problem is solved before we solve our problem. So it's kind of counterintuitive, it seems, but it's the best bet for doing this. You don't genetically them all. You do be cute. You make them cute, but cute for us and very scary for the rats, or the mice, the vermins, and scavengers. That vermins are like the things that scavenge. Basically, a scavenger is a vermin. Basically, rats are scavengers, scavenge after us, and the mice. The mice scavenge with us, and the mice scavenge with the rats and all the vermins for our food, trash. And the cats eat the mice, but they eat our shit, all the mice leave over. So the mice eat what the cat leaves over, and that's including the poo, and the nonsense they do going around the poo, And then the mice, whatever the mice eats is less, like something's alive. What's the nuts, all the things that squirrels eat. So squirrels are related to the mice, but they are not vermin. A vermin is like a squirrel. Because if you give a squirrel a nut, nuts, they eat some nuts. But we don't attack them with nuts. We share and eating nuts. But rats eat a lot of nuts because they can eat nuts. Because they're vermin because they eat nuts. Because they eat nuts, we can eat nuts. But cows can drink milk as well, so we can drink milk. So that's the idea. This kind of in vitro fertilization process is like indirectly. So if we can reach for 2 levels, we don't need to touch any more levels. So if we can get the rats to never eat anything we eat, then the rats are already have to eat what the cat eats, and that's other things. Even the milk, because cats can't drink milk, but because they have to drink milk, all the milk, cereal, nuts, all the things we have. No, it's not really down to the rats to eat it. It's because the process they need it. They need to eat something. You have to eat something no matter what they do. We want them to eat nothing, next to nothing that you eat, or nothing at all. So that's the idea. You don't force the rat to do it directly. You give them some kind of layer to work with, work with and against, and obviously so to be scared of us, why should be scared of? But they're not scared of us because our homes are dirty, homes are like a paradise to them, our homes, our paradise, our environment is paradise. Literally, there's no cats here, even though all the cats are stray, it's a paradise to them. They can walk past the cat, oh, this is a cat, oh, this is a cute big rat, the biggest kind of rat. It's so cute. That's what they are thinking. Obviously, they don't even think about just the rats are even some of the cats that scare the rats. They are what is this creature? I don't even play with them no more. It's like it's like we don't have to use the model. But this is what I'm trying to model in the area, like business opportunity. In my constitution, there's the policy that only neurodivergent people, open access, GitHub pages, everything's for me, neurodivergent only. I don't care no more. But I care for the people that care for me. Basically, this is the cytoplasm around the whole system. Basically, cytoplasm is just like an under layer here. Basically, you got this model, the zone layer. Basically, this extra, basically, before the cytoplasm, this the area, because you don't know the because you don't know the angle. So, one more thing, basically, the nucleus is very important to understand. So, before we begin, let me just continue. So, this is section 1. Section 2, basically, basically, this is what the model here. So, this is 5 stages. 5 stages, but the moon is, so this one is actually this one. Hatching, but I don't know. Oh, my pen to go, I don't know. Oh, the pen looking free to do, I don't know. Anyway, Namji. So I got my model here. This was up here. Let me continue. So, my pen, I can't write down. Let me say, when you can think about this, this I'm trying to do something of DAG. We should got a paper here, but the DAG is one-way DAG. It's kind of like interesting to call this a one-way DAG because I've never seen any. Because basically it's a heterogeneous, homogeneous DAG, which I'm gonna give you. Are we gonna work it out here? If I'm gonna go to pen, which is the problem I'm experiencing trying to find that pen. But I'm gonna say it anyway. So if you can build something, you can break it. Anything you can build, you can break it. Anything you can break, you can build. Build it. If I can break this laptop, I can build this laptop. If I can break my phone, I can build my phone, but it takes time. If I can, that's the first thing. If I can create something, I can destroy it. If I can create a sign, effect, I can basically cause an effect. If I can create an effect, if I can cause an effect, I can create an effect. Digitally or not, some kind of system, computer or not. If I can destroy, if I make something noiseless, I can create it. So 2. Now, those things are inverse conjugate. They work with each other and against each other. Create and destroy and create. In all aspects of our existence, 3D space, we can all do those things. And create, repair. If I can renew something, I can repair it. If I can repair something, I can renew. Because basically, that's the same thing. So you can repair something, I can just keep it and renew one. So that's the problem here. So basically, the quali model is space-time bound. So basically, my space-time model is literally on lattice modeling. What does that mean? Basically, lattice is only have 3 operations: union, disjoint, and intersection. That's for static systems. But the plasma system in the other video is based on this lattice model. So a lattice can give dynamic properties, can have dynamic properties. Basically a lattice has dynamic properties because, for example, a lattice is the union of two sets. So if the model is sparse, that data is sparse, that model is sparse, then you get a sparse system. Can be no matter basically it's like a walk cycle. I can walk one way, other person can walk another way, but we don't walk the same way. Because there's only isomorphic layers of walking, but there's many types of walking I can do. I can walk like my back straight, fully straight, upright, I'm fine. But someone else can walk upright and have some kind of back problem because that's not their unique way of walking. Basically, language is demographic. Basically, similar language. French is not English. English is not French. But because I'm using English as French, because we have Latin, but we don't have we have Latin in the sense we have Latin Romans systems here in the UK, but we don't have that in any shape or form in the Anglo-Saxon. So basically, Anglo-Saxons they have their own way. Anglo-Saxons have their own French. Inventing French, we got Russia, we got all the Anglo-Saxon area, and we got the African one. What's African? The Sibidi, the Biafrans. Actually, so basically, those are who built the foundation of Nsigi, basically Sibidi. But there's no direct connection to them, but they share the same isotope. So isotope are kind of the sparse definition, basically Biafran history, isotope layer, they share the same size, unit size, or fractional unit size, but they don't have they just bridge out differently. So I can speak French, you can speak English, but there's no connection in that homogeneous space of what is language. or what definition, what consumption verb now conceptualization of instruction is languages. So that's kind of the idea I want to give you. It's like you don't do this. So basically, this is model here. This is what I'm saying. So you get this video here. So basically, this is the video I want to show you guys, but I don't want to show you guys here. So this what is basically you get a Fourier transform. So basically, the Fourier transform is used here because you get lattice models, duplex interpretation, two interpretations of system like Python and Lua. Lua interpretation. You get two different sets of information. Like I can write in an interpreted language, Python. Now Python can be Lua. I can write in Python, I can write in Lua. But these are two interpreters, but they use a different concept, different language dialect to speak. Now, the dialect is the unit. So basically, I can speak formally or informally in two contexts, based on how I'm in that system. Context switching, what I call context switching, because the context is different in the language. It can be structure switching, but the context is the Lua and Python, which is interpreted. So basically, they work on different protocols, language-bound protocols. But the protocols, so if I'm talking from Lua to Python, there's some things I can't understand in both systems. I can't even see it or comprehend it because Lua has speaks its own tongues. But the parser system has to recognize the system for the polyglot system. For example, if I'm speaking from Python to Lua, without any polyglotta, I have to interpret Python too. So from Python, Lua to Python, from Lua, I have to interpret Python. That's a must, guys. I have to interpret Python. By interpreting Python, I have to instill its essence into my not necessarily. I have to change. Example, let's say Python. Get the Python. How to define a function in Python? Def main, colon, no indentation bound. Indentations are the same thing. For same function. Right, left bucket, XYZ, function main, colon, do, and then end. That function does the same thing, but they work in different signatures. So I'm saying, I'm not claiming, I'm telling you, the dialect is different. The function keyword, main, and the def are defined functions. These functions are auxiliary components, because the auxiliary layer is the definition itself. So basically, auxiliary means you have two interpretations. You have basically it cannot be this or this, but the interpretation is chemical. So they mean what? Function. Define a function. Then you get a main identifier. Main name, the main entry point, and brackets are like the parameter block. The tokens that indicate the parameter, and then do is Python's colon, and then end is end or pass. End or pass is because you have to put that there. Pass means you skip through, or end. The same as some layer to it. Now, if I send this block from Lua to Python, I will not know what it means. But if I get the clinical state of this lexical analysis, I can invoke that function. I can call a Lua function without any overhead. The interpretation is fluid. There's a verbal modeling of the sparsity of what I was called. But it doesn't say. So this one I'm saying here, the cycle thing. So basically, this here, the Fourier transform is for basically this is Fourier transform. This is a combination. So you get x, y, you get a simultaneous equation. But we give something called a Fourier transform for lattice. So basically, all systems work on lattice. The lattice is just the lattice is just the standard state of superposition concept for the data model. It's got lattice space, and you got like a polar coordinate system. You can get a polar lattice or a Cartesian lattice. Basically, the system, polar lattice is kind of cool now. What we use the bubble call it, but we don't usually use Cartesian polar lattice when the data is sparse and stable, like it's stable and secure. It's stable. It's not. It's very static, but it's a sparse data. This is sparse. Use a polar system. It's precisely accurate. Basically, the Cartesian will not do it. But the lattice is not good enough for dynamic. So this is why you have Fourier transforms. Now, a Fourier transform is the same thing. It's dynamic transformation. So that's what you're going to use for basically sparse dynamic transformation. So you can do both. So if you have a matrix sparse dynamic, you can transform between Lua and Python because Python doesn't need Lua to do the same. Example, The lattice, basically, if you align the lattice to be the sheer canonical state of symbol of definition identifier, obviously, function keyword, keyword space. I can't find my pen, so let me try to write it down because I can't make a mistake on the computer now. So let me try to do so. Right, basically, the sheer canonical symbol. I love you, turnstile. So basically, function do function main args. So we could get the dot args. I love Lua because Lua is dot main args or dot arg main var main give me a second, main function do and you get def main do n. Then write down and you get no inputs. Let me do pass. So what the input of Python? Python is dot key var args key args keyword args. So keyword args. So basically keyword args. This is and this is the same thing as Python basically keyword and star args. So star args is like the argument. Is the verb. Star args. Start keyword args for dictionary and star. What's the main input? So main inputs are very reductive. So you get the same thing for keywords. Because basically your machine repo, the args in the basically get under var args, you get var args, v args, which is the standard one for standard input you do very reductive args. We can have dot very args, which would be dot very you get why think of you get dot args, dot args, and dot v args. So you get the function function main open bracket dot args, comma dot var args, and that'll be close tuple and then do n. But this is not good enough. I'll come back to that why. I get def main star args keyword args. So this is it basically. But basically you get all of this, but you don't it's flexible. But this what I don't like about this is because you got like the color bracket tuple. Now the tuple input is like why could I have the main take an array and that represent the array? Basically the tuple is just ordered and indexed. And that's what I mean because this definition is kind of indexed. So basically it's ordered. That means homogeneous data can be put in there. For example, heterogeneous data can be put in there. But based on the conjugate pairs. To get heterogeneous data for that, but this is basically it's better to have a sparse definition. So if I have def main, it should take the input array or set notation or some kind of other way. Depending on how you're gonna invoke that function, that kind of thing Gaussian likes me to do. For example, I can define this as a canonical state. The keyword is equals to keyword. The keyword equals function and or def, and you get function then, and we get space, which is the nil space, nil or blank space, nil blank, which is space, and we get main. And the main identifier for the program name called main, and this basically and we get the input to the kind of data model. Basically, the kind of problem I have with this because the input is non-isomorphic, so the lattice is bound to the geometry of the system. But basically, the geometry is like a expression of what a Python calls an array, what Lua calls a dictionary, what they call each other, how they interact based on data models only. Because data is the best way to model it. So this is what I've got here. So you get var arg, come out var args, come out do and get colon pass. So the pass is like yes, the pass is the end of Python. So that's what it means. Oh, the pass is when you pass something, you're terminating the code. But the print instruction, basically, this can execute. This is what the bridge is between Python and Lua. So basically, I'm trying to implement this kind of polyglottic chamber. So there's no fragmentation in the set space. And how this works, basically, this space has to preserve. If there's no code, there's no channel. Basically, there's no layer to transpose. Basically, this is an auxiliary component of O1 for sparse data model, sparse space via bubble qualia. Basically, this just means basically, example, basically, because so basically, how this works is that so you get, example, say you need a space of 20 bytes of you need 16 bytes of memory. 16 bytes is what? 2 bits. Two bits. Two bits shared bits. This can model. This is a hexadecimal system. So you can go 0 to 9, 9 to 0, and then you get A to F and F to A. You know, F to A. This is basically the first two pairs run from decimal 10 to 16. The second pair is 10 to 16. 10 to 16, which is A to F. But 10 to 16 can be indexed as 16 to A, 10, because you know that's A to F. F, okay, not A, B, C, D, E, F. Oh, 10 to 15. 10 to 15. Basically, 10 to 15 is the mapping. So it's kind of indexing it and transforming it back into the input of numbers without even processing the nil operators, you know. But the idea here is to develop a polyglottic protocol for Golang and all the things I'm building. So there's no the color composition is preserved. You know, that's just the information protocol. You know, our user states, so the nil states are there, you know, for nothing else. But they are modeling the data structure and the sparse model of the system without being directly involved in the process. So if you send anything over an A star protocol or some kind of semantic vector in X, A star protocol, you get A star scoring via Hamiltonian and Eulerian notation, which are synced in a bi-directional component or duplex string. So you can send, but basically there's no consistency needed here because it's just standard canonical shared chamber for protocol messaging via you get the GSI gossip just gossip I integration and M for message. So the message and this is just fast format. In Gossip, you get the standard iota.ts files, which you write in. But you can use the message files as a canonical state for messaging over networking, but they're tomographic, which just means they work on they care about area first before they care about the actual parameter via open derivative system. So so the first system is just the convolution. Now the convolution is the same thing. Basically, the convolution it just means so you get a standard multiplication, which essentially, if I get the identity matrix, I have to perform the transformation as the sum. Let's do so. Get basically to get the first pair of A, you get AF, FA, you get FF, AA. So basically AFF represents 15 times 15, 15 times 15. Or in hexadecimal or hash 15 times 15, and that'll be the FF, and then you get FA, which is 15 times 10, 15x10, 15x10, and you get AF 10x15, and what this is a 2 by 2 matrix of pairs of paired matrix. So you get 2 by 2 10 times 15, and you get 150 a shared frequency of a space you need to compute over all these sets, and then you get 10 to 15, you get 15 to 15, and you get f times a times f. The canonical operation is times in binary. So this would mean that but this is what we're trying to work in a binary now. So basically 150. Basically this is just January. Because you just do binary, but in binary, we have to do binary, so we have to convert this 150 to binary, and that'll be the same thing as basically because it's hexadecimal. If we ensure the rotation from the axis based on polarity, 15 to 0 is 15 to 10. You get this preserved space for computing over A to F. So to share this basically, for example, so that means you get 15 times 15 normally. What's that? 15 times 15? Or 15 times 15 times 2. You get 15 times 2. 15 times 15. 15. Which is 15 times 10, 2 to 5. 2 to 5. And you get 10 times 10, 8 times 8. You get the maximum times the minimum. So this the 8 times basically 3 times 15 is f times f, but you want to do basically this can work out to determinant. Now the determinant of 8 times f a times f is 150. So you get a b c d. So a times b ax c equals a is 10 times 15 10 times 15 equals 255. Wait, 10 times 15, which is F, and then that'll be B will be halfway, so A, B. But it's not B here. So B will be the second pair, that'll be F times A, that'll be A times F, B will be F times A. That'll be F times A, that'll be F times A, because it's A times F. That'll be the opposite, that'll be A times F. That'll be 2, 2, 2, 5, 2, 5. Then you get this. So you get A, sorry, 10 times 5 is 225, and then 8 times F, and then and that'll be 10 times. Wait. So you get 150, 2 pairs of 150, 2 pairs of 150, which is 150, 150, which is a vector, or one input, and you get 225 squared, 225 times 225, which is the pairs, the shared area, the shared perimeter. So the first transfer meant to do that. So this is past model of the bubble via the efficiency rule. So basically, I'm not done yet. Yeah. Oh, this is I've got 5 more minutes. I have to make another video of this basically. But in the 5 more minutes, let me explain to you one thing. So in my next video, I will like come back to my paper here. So this is the full model here. But they didn't really give the bit of the footage of the bottom burner. But I'm going to define the security model from the system. The security is basically bound on the security based on the fire, the bubble model. So basically the bubble model is meant to ensure that the bubble is there. For example, basically you get the bubble here. Basically you get two axes here. So we can get the up and down. It's like so you get a fold. So basically you get this is a straight line. This is a straight line. And you get a projection into the, so you get x, y, one x coordinate, but it's polar, so you get the y. But the y has to fold in after, not folded. So you know how folding is policy. You get like some kind of rotation. So the rotation has to be a polar axis, based on the right hand rule or the left hand rule based on the axis you're modeling, and that'll polarize itself up. Because one thing we really do is define because I'm in a bubble world, bubble universe. Basically I'm in a bubble. So the bubble is like the mind, the bubble core system. So you never have a rigid corner. You have basically this rigid corner here, but you are meant to shape into a bubble. So you project yourself into a bubble. So this is a bubble here. So basically you're meant to define some kind of Bunsen's curve that models the fire kind of fire in the system, the fire of burning, the Bunsen burners. And that will literally make sure the Bunsen burners are never. Now the Bunsen burners are there, but they're meant to curve with the fire. So the fire is meant to burn without the Bunsen burner. So this is the hottest point. The more you put your hands close to the fire, which is the tip here, the tip where you are constructed, you are burnt. You can see yourself burn. So that's kind of the security model for the cytoplasm around the egg. Because the more you try to break the system, you get noise. So you become broken. And it just takes you hold. It's kind of funny actually. So that kind of thing. So how I'm doing this actually is this. Oh, how am I doing this? You get this. You get you get speed. You get this create update read update delete. Create read update delete. So basically this is the model here. Create read update. This is basically a Cisco bound because Cisco is right left rotate. This is an architecture model for the quali system. So you get a security quali model. So you get create root read right read update delete. Get that to get read, create, and you read on your right, and you move to your go to left, and you go to the right, delete, nil. No, basically delete. Basically, you delete it. That's the last option you can do, and you get that nil. So basically, on the right node, you have right. And when you're reading something, you can delete it. Basically, create, read, destroy. But for like create, read, destroy, you can get repair or break. Or this is just the first model. Repair something, break it, or use something, repair it. So you get this model, so you can use this model to construct the read, control the delete. The inverse one. This is nil, based on the bottom up parsing. So this is Hamiltonian initial resolution. You get the model. So you start with the reading operation. You can write or update, and then write and then go. If you can create something, basically, if you start with the creating, you can update it and delete it. But you have to do either one. So you get you can't have to go back once. Basically, you get a nil, which means now, which is like the wait pointer, to 9. But then nothing can be execution. So the problem with the whole model is that nil is execution. So when you nail something, you can't execute nothing. So nothing is just there's no seed to start it. There's no input, but you can have a nil start. So the new star is a user space and time, everything and nothing. So the new represents everything and nothing. So this for this to work properly, you have to get the state here create to read, delete to create, destroy. You have to get everything which is the bottom to nothing, which is like read, create, read, update, delete. You have to update your state, kind of that. So basically, read, write, execute, but for genes, genome. Genomes, genomography. I'm calling it it's radiography, not calling it geomography. It's about understanding ourselves, ontology. So that's the idea then. So, this has stopped. 1 second, guys. So basically, I'm trying to. Basically, I'm looking at auto AI, guys. 1 second, I'm looking at auto AI. So guys, let me just try to make a video. Auto AI is now starting. Is it starting? Yes, yes. So this embryo 2, EM2. So EM2, yes, basically the same thing as I'm saying is the cytoplasm represents the state of the consciousness of your tomography, which is area, not surface. So the area of this is 1. So basically you get 1/2 row, but that 1/2 row, everything's a half. You get a half row or a half ratio, but you apply them when you need them. For example, because space and time, you basically can get half of space, you can get half of time. In the real world, basically you can have a half byte or a half word, which is the assembly equivalent of half a byte. Half a byte or half a word, which is the byte. Basically in my model, you got half a bit. You can't have basically you have half a bit. Half a bit is the inverse conjugate, so you can get half a bit, or you can get, but basically you don't drift from the ratio model. So if you get half a bit, I'm just calculating right here. So in my assembly language, you get half byte, half. You can get one full whole, and you get a half of it. But when the zero step with the point with stop, so you get the inverse of half. To get to you get a unit half. You get a unit full, which is -1. Now the -1 is you have to be opposite, the polar opposite of 1. So you have to go to -1, but to do you have to get the half of -1. So you get a half of 1, half of 1, half of 1 is a half of 0.5. Now 0.5 is just a decimal representation of a half. Now 0.5 can be used to scale downwards. So you're now half your size, and then you now get scaled upwards. So you have to scale 2. So you have to scale half. So a half times 2 is what? But 5 times 2 is what? Equal to 10, equals to 1 and 2 and 2. Half squared is equal to 1 half times 2 is 2. So you get back to 1, but this one is not 1. So you want a half times -2, so you get a half times -2, -2, and this would be to scale up. You get -2, you get -1. Now you now have -1, so that has a conjugate inverse of 2. So this is a half rule. So the half rule is a ratio you seed into the system. Now the half rule is very important. You do now you get a half rule. Now to get to 2. Now you're at 1. Now you are at 1. Now you're at 1. So you went from the 5 to 1. So what do? You halved and you scaled by the opposite, the inverse. And I'm saying this is why the inverse distribution matter. The opposite of the opposite, the half and the opposite matters. Now you are at 1 or -1. Now this -1 is the whole of the other system, whole of the womb. The womb of the embryo of the womb, because we go through you get to basically get before you start when you get into the days, before you get to the days, you get into 1 week. Now 1 week can be rapidly become a month, but 1 week is a month, basically. 1 week you are going to be the 1 week you get basically what's the 5-month embryo development. Yeah, basically let me try and find it now. So 5 months. So you get the 5 month yes, you get day 5. Day 5 is 5 days. Now, how many 5 days a week? 5 times 10. Basically, you need a chemical state to do this. Obviously, you have to have chemical time or C time, and C space and time, because you have to separate space and time. The space is the egg fertilization, and the time to do it. Because if those two mingle, you fragment the whole system. You need space and time separation, because so the space of the embryo is 15. 50, but the 1 unit egg, the 1/50th of the egg is a sperm. So if the sperm is one space of 1 unit of the egg, you get all the space and time to model that. I'm just going to show you how to do it here. So we're going to do it now. So example, that's usually with this done, and then so you have to manage them. Basically, you separate the operations from the actual thing, because the operation worked on dimensions, and the dimensions are space and time, which share half properties. Which is why the half ratio is mandatory and not a requirement. You go a gene pool basically. This is like a mini gene pool. Because one gamete is one gene pool. One gamete is a gene pool, but the gamete can sustain itself. If the gamete can sustain itself with 10% of what it resources, then it can become a full born, full zygote, which is a baby that's born, in my model. So I'm saying that 33. Oh, I'm saying that for the chamber, we have to try to do that. So basically, you don't even need stability. You don't need to do anything. The chamber will do everything, because the chamber makes sure the stability is there and you can do it itself. They just basically the same basically section 2. Basically, the gamete does this. Aries biaticity, this is the biaticity, this is the error, and this is the hatchling. But don't worry about this basically. You get a timeline and sizing. So basically, I got a rule here. So you get noise. The noise is just a sign. Basically, you see this nuclei. You want it stable. You want it stable. So you want it to only create itself. This has a nucleus. You see this egg, it has no nucleus, but it is the nucleus. It is the nucleus, and the egg is its own nucleus. So when you have two crates, you have a pair of crates. So we can create something indefinitely. So we can be born over and over again. Rebirthed via the cycle model. If we not do it, I don't think so. Actually, I don't think that's true. But theoretically, hypothetically, it's true, because the egg is an embryo. The sperm is the inverse conjugate of the embryo. Can be. It's just the same thing, but you get half and half of the shared DNA. So you get one full whole human zygote when it's born. So zygote is perfect, because it works. When you're perfect, you work. You don't need any support, which is idea of the same no policy you need, because you're just free your mind. So this is like I'm saying. So the gradient of the IVS is the cleavage. So you get this is basically the embryo. But you see this so this doesn't really matter where you come in, where the sperm comes in. It starts to seed in. You can have two coming from any angle, dimension, but space and time, no matter, but they're the same thing they're doing. So you can have two child, this doesn't matter. As long as the egg is fertilized and the isolate is stable, it becomes a plasmoid system that is stable. It becomes you in physical quality, in physical form, via epimus. I don't like inverse. I don't like all of these things. Here. Oh, the 7 minutes. So I go computation here. I'm going to give it a go. So the sparse density of the system is the data structure. Okay, dense and the sparse, what's it called, unit density. You get basically, you got the dimensions, which is the one-way dimension. It's one-way process. This is one-way process. Basic dimension in the 3D world. It's one-way process. We create once. We can get something all time. Basically, we only see in time. Basically, we can only observe half of a dimension above us. For example, because we're a 3D being, I can use all my tools in my reality. I can see everything in the dimension, my dimension, space time. If I by just trying to, basically, if I separate them properly, if I treat space as one dimension, I get one dimension of space and time. But that one dimension is fully one. I can see properly because that's time. So you can see all of my space based on my place in the universe. Half time, one space, and that'll be one time, one space I observe at a time, or one time, or the full time observed at space quantum bomb. So basically, that's space time continuum. But I get a fraction of that, because I get a fraction of the dimension above me, because I have 1 unit of dimension above me. So 4, let me do 4 minus 1 is 3. So I lose the dimension if I want to observe. So what would the dimension would be? No, I don't see the dimension, so I get a half or so. Half of 4 is 2. I get half of the 4. Half of the 4, which is space and time split. I can look at it at one time. So I can look at space time half split. So I get half. That makes sense now. So you get no matter the dimension I'm going to, because I get half of the dimension because it's 40. Now, for me to go up, I have to double my resources. So I have to get space and time together. So that'll be dimension I need as 1. So I get half of half, and then we get minus half of half. And basically I get the opposites of the system. So I can use the one hole measuring, trying to observe the reality of the system. But now I need the opposite fraction as well, because that's half of half half, just to measure things properly and ensure they are fully coherent. So if you get minus half, you get plus half. And that's the idea. So you get two halves in one hole, and that's the idea for negative and positive dimension for two scales. So the scale, so you need entire dimension, you need to be in the four dimension realm. Again, but that's the idea. You don't fragment anything. There's no fragmentation whatsoever. There's just coherence. Just understanding based on ratio, and bracket system. But look, basically that's the idea there. Is there anything I'm not covering in this video? Basically this is binary calculus. Is there anything I'm not covering? ASCII table, no. My business. Yeah. So basically that's not what I'm looking. This is a risk architecture bound. This is CISC mode, but all CISC can do risk. So what I'm saying to you is, I think 40 minutes gone. 1 second. 1 second. I think I have to do this now. Okay, so as I'm saying, so you get that model there. You get the sparse model. So adenine is capital A, this model, but adenine thymines are all capital letters, or the big ones, the big adults in them. But they model heterogeneous states. So if you have two lowercase a, adenine, you get male, female. So you get the adenine of female, adenine for male. Adenine makes the zygote. Okay, are you a female or male? Are you a quality, a mind quality of female or male? And then the other one, thymine, can be physical model, but they work on the same principles of body and mind. And get a pair. Adenine pairs with thymine. Thymine is guanine. So you get full thymine, full madam. And get thymine. And then you get size in guanine. So that's model there. So basically, you get adenine, thymine. This is the model. Basically, this is the same model. Because the right root, basically, the right root is the same thing. So the model you get, if you this sequence question. TACG, basically adenine thymine gives you what adenine first. If you're pushing adenine first or thymine first, depending, basically if you're pushing thymine first, I'm pushing this side, so you get thymine first and then adenine next. So basically if I have thymine and there's no adenine, I get a nil association. The placeholder A is there, adenine is there, so there's no fragment, there's nothing there. So if I know thymine is there, I can put either thymine or thymine. If I want thymine, it's just a thymine first. If I have one thymine, it's two thymine. If I have one thymine, I have two thymines already, because I don't put anything. I just put a placeholder of there. But basically, the placeholder thing is thymine bound. So the nil operation is just, if I put a T on the right, and there's no T on the left, that's just an xt, or unit state of T. But how do you know it's a T? So basically, if you look at its current T, and you put T forward, but you don't have to look behind it. Basically, the T model, the thymine is there already, but you have to execute it. For example, the structure is basically you have to create some space for it, and create some time for it. So even before the execution does it, you have to do some called pre-flight checking, pre-flight parity checking. So this can be literally. Let me just use binary states to do it. Actually, let me just let me try to do it for you. So you get the pre-flight binary. How this works? So you get 0, 0, 0. And 0, 0, or 0, 0. So you get two states of iota, two states iota. You get AA, TT, AT, TA. So basically, what you're gonna do is A for so when I see one T, I know this T is can be either two states A then T or T then A. But because I have one T, I have no states before it. This will not resolve. So I put an X in brackets for execution. So this is executable data structure. Basically, it's just a placeholder that means something if there's nothing, because it's pre-flight, so it works before the system works. Basically, the system can resolve itself over protocol without. So if I see a T, I get a T, and that means the T is what? A T first, the T prior to the T. So TT, I put a T there, and that'll be T because that'll make big T. big T. Now this big T is same as TT. So TT equals big T. But this other model is just one factory. So big T equals TT. And now big T can be big T can represent A or T. A small and small a and small t. If the inverse is there, if it's A then T. If the inverse is A, big A. So this big A represents small a and small t, and small a and small a, small a and small a, and you get small a and the t will be basically the t sparse state will be big T will be equals to T then A, and an A then T. T then A and A then T. This would be the encoding table for pairs for thymine to resolve itself, over the pairs of adenine. So for this to be really working in the sense, you have hops, groups, everything. So you get this table here, the sparse table. So these AT states are really all you need to get to real ionic state. Basically do pre-flight. By pre-flight, I mean you have to do it at the protocol level, even before the protocol knows. Because the protocol doesn't know what it's doing, what it's gonna do for you. It doesn't know what you're gonna put it into it. Doesn't know what you're gonna do. And that's the main problem here. So you have to create some space around it. Basically think of it like so if I need a 16-bit if I need hey, stop! If I need 16 bytes, 2 bytes to store 2 bytes, this is 8 bits, 8 bits, 2 pairs of 8 bits. I have to think about the space to store this information, and that is doable based on how we encode it. So let's try this first, because the AATT. So AATT. So you get 4 states: big A, big A, big T. So you get 4 states: big A. Minus big A, because minus big A is just the inverse of A, and then big T and minus big T, which is just the conjugate. So you get 4 bytes to encode, 4 pair bytes, 4 times 4, which would be like 2 bytes. You can start with 2 bytes, which is 16, which from hexadecimal is 16, which are 2 bytes, 2 pairs of 4 bytes. Or 4 pairs of 2 bytes, and they share a user state of 2 bytes, which is 8 times 4. So basically, 8 times basically get 2 bytes. Let me calculate here. So a byte is 8 bits. So 8 bits, 8 times 4. So basically, A times minus 4. No, sorry. Basically, you get the representation. So you get number minus 8. Minus 8 times 4. Minus 8. Minus 8.
So yesterday what Wally did? Only night.
Minus 8. Minus 8 times 4. Basically, minus 8 is 1 bit. 1 byte. Minus 8 times 4 will be minus 32. Minus 8 times. If you get 8 times 4, and you get minus 8 times minus 4, and you get all the operation done. If you get 8 times 4 is 32, minus 8 times 4 is minus 8 times 4 is minus 22, and then 8 times 4 times positive 8 is 32, and minus 8, and basically that's the range. So you get minus 32 to minus 8 and minus 32 to 8 based on the heterogeneous homogeneity key value pair or indexing structure. So the idea is that so you get that for the big thymine layer. So because there's two you get 16 for 8 bits. So you get the range plus minus 32 plus or minus 32 over the set of 64 space. So this will just compute the space you need before you actually need it, before you actually send the message or the packet via the quali protocol. Now, I haven't really explored the quali protocol, but I'll explain it later. It's kind of very good long video. But the quali protocol is literally like a spring. For example, you have some kind of time, auxiliary time, but you're gonna know the time ahead of time, which is kind of funny. So you compute the times from the space via Rift tomographic system. But I'm trying to do it. So we just try to give it. So let's say I have some. Let me compute it. So I have 64 by 32 plus 32 is what 32 plus 32 is 64. Now 64 to the power of 4 to the power of 4 will give me 64 to the power of times 4 to the power of 4 is what 256. Now 256 states the program can be. Now I get pi. Basically, I'm trying to define the Corey algorithm. Now 256 bytes of memory. Bytes of memory for his decimal resolution. Now, this 256 basically I get basically this 250 is the canonical 360. So I have basically using the quali model 256 divided by 360 equals to 360. 360 because this is just the area equals to 1 unit, but the 1 unit of 360 is just 1 unit, one a unit, not like 1/10. Basically, it's very important to have the 1 unit 10 100 model. So 1 unit, so 250 equals 256 equals, and you get the pi 3.14, which is equivalent, and you get pi times. You get pi 3.14 here, and get the radius. So the radius of what I'm trying to compute is what over these spaces, what the radius is half of the basically the radius is the pi, but the diameter is the radius, pi r squared. No, that's basically that's unit of pi. Radius is what I define. Radius equals 10. Radius equals but 10 what 10 nanometers. 10 nanometers. Nano is 1,000. Nano thousand. Yeah, so 10 nanometers is 10,000 with 10 to the power of minus 10. That's 10 to the power of, really, if I use 10 to the power of minus 10, that's 10 10 to 10 kilo, but in plus you get 10,000, 10 1 2 3, which is 3 zeros. So 10 to the power of negative 3, 10 power of negative 3. So basically 10 to the power of negative 3 is what 10 1 2 3 4 times negative 2. That'll be minus 10,000. Basically, that'll be minus 10 0 0. So the idea is that, so you get minus 2 0, and you get 255 equals to 0. So you get the unit model. So 256 divided by 256 is 1. Share one state space, and more 10 divided by 360 is what 227 times 77 times 3.14, which is pi, and that gives you 1 unit of pi. Now that's pi. Now get over 360. Now 255 divided by that'll get 87.26646. Yep. Yep. So that's what I'm saying. So the idea is you literally separate everything, and now we can cut off between A and B. So basically, when the model is done, it's half time. It's polar half. So instead of using 360, which is like one full complete system, you half it. So the half of this will be or the square root of this is half, based on dimension. So the half of this will be the half of number. If I divide it by 2, divide by 2, that'll be 43.63332312. That's 43.63333, and that'll be the half system for dimension I'm in. So basically, if you don't understand what I'm doing it again. So go back to the chapter. So basically, I've just computed the space or bytes I needed to store, to reserve for 64 bytes of memory, which share a state space of all the program and the time you will need in parallel, all in one go, which is 256 bytes of data. Basically, 250 bytes of data means 256 bytes of data for space and time, whatever the program needs to do, based on the canonical position and separation of confirmed for parallel process only. Should never share states for continuous switching. In this video, almost 60 minutes. Yeah. Let me end it now. Thank you guys for watching. Basically, I'll come back to that. Thank you guys for watching.